All right, more 3D stuff. This is just kind of like the last one, but now we're talking about pyramids and cones. Pyramids and cones are probably things you've seen before. The main difference is we're talking about pointy objects now. We're not talking about sort of boxy objects. We're talking about objects that have one base, and then they have triangular walls that go up and go up to a point. And just like that last unit, or that last lesson, there's this cool website that does all these cool different versions of this. This is a pyramid that has 7 sides on the base. You can see that there. This little red segment is not an edge that looks like the rest of them, but we'll talk about why they do that in a second. And of course, you can still make them more see-through or less see-through, and you can pull them apart. It's really kind of cool. These look like birds to me for some reason. And you can adjust how wide and how tall they are. Oh, and here the tall thing does that. That's really freaky. We're not going to do that so much. We're going to mostly stick with things that go all the way to a point. But anyway, that's the kind of thing we're talking about. Let's make it a little more like that. Okay, so there's a pyramid we're going to come back to. Okay, so a pyramid is a solid figure with a base that rises to a vertex. So that thing at the top is called the vertex. This pointy edge over here that you'd stab someone with, that's called the vertex. And the lateral faces are all triangles. In fact, most of the ones we're going to deal with are all going to be isosceles triangles. Yeah. And again, that red edge looks a little funny. I can sort of get rid of it if I do that. Now it's not see-through. Maybe it's harder to see what's going on there. Oh, I know I could do this. I could make it wider. It would look a little bit more like an Egyptian pyramid. Okay, great. We'll have solids of these in the classroom too, so you can see what those look like. Lateral faces this time are going to be triangles. They have lateral edges. Lateral edge would be like this edge going up the side, like edges going up the walls like you're used to seeing in the prisms. And that thing along the bottom is called the base. That's the thing we're changing the sides of. So right now that base is a hexagon. This is a hexagonal pyramid. Okay, and these triangles are called lateral faces. Okay, the altitude of the thing is not something you can see right now because it's on the inside. The altitude would be like if you were going to sit it flat on the ground. Can I make this sit flat on the ground? Kind of. It would be the actual height that this thing reaches up into the sky, which is kind of hard to measure because if you had this thing solid in front of you, you couldn't measure it really kind of on the inside. You'd have to make something else that's exactly the same height off to the side here. If we make this a little bit clearer, that red thing is not the height. That red thing goes along one of the sides. You see that? The height would go like from this vertex straight down inside the center here, perpendicular at the center of the base of that hexagon. All right, well, those are fun to play with. You can play with that link, again, from the link from the other video. Okay, what we're mostly going to talk about is regular pyramids, where the base is a regular polygon. The height goes straight up the middle. It doesn't lean over like this. There are such things. They're called non-regular pyramids. We're going to deal with the regular ones. This could be a regular pentagon base, regular octagon base, equilateral triangle base, but the vertex is going to go straight up from the middle of that, which is nice. There we go. I think that's everything we need. Oh, one new term here. This thing is called the slant height. This is a very important feature, vocab term to label on here. And you'll notice that was the thing that they kept showing up in red along this. If I make this slightly clear, this red one, I don't know if you can tell it's red, but there's this one, and they only indicated on one face. This is a hexagonal base, but for this one side over here, they decided to cut this bottom one in half and draw a midpoint here and draw this up along the edge of the side of the pyramid. It's easier to see if I do that. And that is incredibly important because that is, if we wanted to try to find the area of this one side of the pyramid, we would want the height of that triangle, and the height of that triangle sits out here, and it's different than the height of the pyramid, which goes down the center. So it's longer than the height of the pyramid. It's shorter than one of these orange edges that are actually there. Remember, each one of these in a regular pyramid, each one of these lateral triangles on the lateral wall faces, they're all isosceles triangles, and this thing, slant height, is actually the height of that triangle if it were sitting flat on the table. I've got that drawn a couple other ways. It's a little easier to see. This is another picture of slant height. This isn't a great picture of slant height. It almost looks like height. But this goes from the vertex, like you're sliding down the mountain, and you go right to the midpoint of one of the sides of the base. That, you know what? In fact, I could make it look like that. that length L there, what we're really talking about is it's be the same as going wee, whoops, I was a little off, going wee down the side of the mountain, right down the center of this side to this midpoint down here. We use the letter L for slant height because it's one of the early letters in the word slant. Slant height has an L in it right there. Anyway, so that is slant height. The regular, the height of the pyramid, that's this thing here that's kind of you can measure that here on the inside, internal body sort of the pyramid. But slant height runs down the face. The base is a regular polygon. If we're talking about regular pyramids, the base has to be a regular polygon. Each lateral face is an isosceles triangle, and all those triangles are congruent. Like all the triangles that are part of this thing, they're all the lateral faces, they're all congruent. Oh, we could unwrap it. You could kind of see that. If I unwrap it and lay this thing flat, you'll notice that, what if I do this? All of those faces are congruent isosceles triangles. This one looks a little funky because they drew the height in on it, but really there's just 6 of these. Make it smaller so you can see it. There are 6 of these identical isosceles lateral faces on that thing. I don't know, maybe it's easier to see if I make it completely opaque again, so let's make that solid. Unwrap it. There's 6 congruent lateral isosceles triangles that wrap around, make the lateral area. Come on. I'm trying to drag this down. How it won't work? Oh, now it's going. To make that pyramid. Okay. Okay, great. The height of each lateral face, if we're going to talk about that triangle as a face area, it has a height that's called the slant height. Okay. I know that's kind of tricky to figure out. We'll do more of that in class. Here's another way to unwrap a pyramid. They have this pentagon base, and instead of this one, they kind of unzip it one way, where they just they kind of do that. Let's subtract one side, so it's a pentagon. They did that, so they're unwrapping it kind of this way. So that's open up the box and have all the lateral area be like these 5 triangles zipped together like that. Here they just attach each one at its base edge and just open it up from the top. But either way, we're talking about 5. The lateral area here is the 5 congruent isosceles triangles, and the area of the base is that thing down there. The area of the lateral faces all together, these 5 pentagons all added up, there's a formula for that. Lateral area is, and it's different for pyramids than it was for prisms, it's half times the perimeter times the slant height. Why is that? Well, we can get to that in class, but basically it comes from areas of multiple triangles stuck together. This half in here is kind of left over from half times base times height when we were doing each triangle. L here is the height of each one of those triangles, so that's where that came from. P comes from the fact that we're taking this base and we're taking this many of them. So that's where all that comes from. So that's it. LA is half PL. And if we're going to do whole surface area, what's different now compared to prisms is that if you're going to compute the entire lateral area of a pyramid, you only need to add 1 base. There's only 1 base down here, whereas before in prisms we had 2 bases to worry about. So it's all lateral area plus 1 base. Things you have to think about when it becomes time to take the test. How many bases do we add? 2 in a prism, 1 in the pyramid. All right, this is a little bit better picture of that triangle. With this and this right triangle right here, which I sometimes call the Hal Triangle. Notice why I might call this the Hal Triangle. Not that you'd ever need to multiply all those things in that order, but this is the Hal Triangle because it's a right triangle, first of all. It's the height. Sometimes I refer to this as the height. It's the straight down height of the pyramid. This is the slant height that runs down, skiing down the mountain kind of height. And this is the distance between those across the bottom. Turns out this will be the apothem of the base. Whatever shape that base is, those are connected by apothem. So this is kind of handy to remember that the 3 of these go together in a right triangle. So in fact, if I call it the Hal Triangle, I'll make that a little more easy to remember. The Hal Triangle always looks like this, with hypotenuse and apothem. That's an H. It almost looks like an L. It's an H. The hypotenuse and the apothem are the perpendicular sides, and L is the hypotenuse. That'll mess you up. H isn't the hypotenuse. H is just the height. L out here is the hypotenuse. It looks better in here, but just remember when you're stuck and you can't figure out what to find next on your pyramid, think back and go, oh, have I found everything in the Hal Triangle? Or if I knew 2 things in the Hal Triangle, I could make some progress because I'd know I could get the 3rd one with the Pythagorean theorem. All right, let me start reading this. As mentioned above, the base pyramid is a regular polygon. Regular polygon base area is as it was before in chapter 11, where it's half AP. But then the rest of this is, just about that triangle. That's really, really helpful. All right, cones. Like we made the jump from prisms to cylinders in the last section, we're making the jump now from kind of cones that have polygon side bases to circles. If you just kept adding sides to this thing, add more and more sides. Okay, let me fold it back up. If I fold it back up, let's make it bigger again, so you can kind of see what's going on. Make it kind of see-through, and make it kind of sitting on its base like that. Okay, now if I just kept adding more and more sides, which is this button, add more and more and more and more and more sides, this starts to look like a cone. It starts to look like a paper cup cone or an ice cream cone kind of upside down. It's not really yet, it just has a bunch of sides, but there's actually a polygon down there. And if you open it up, it kind of starts to, ooh, that's not good. Got turned funny. The base starts to look like a circle. The lateral area starts to look like, oh, that's kind of better. Starts to look like a bunch of little triangles like this. This actually starts to look like a sector of a bigger circle, and that's actually true. But right now, this isn't technically a cone. It's just a polygon with like 20 sides on the bottom of a regular pyramid. Anyway, notice when it was just 2 or 3 sides, that doesn't really look much like a sector of a circle. But if you add more and more and more and more sides, this thing starts to look like, those triangles up here start to look like sectors of circles, which is kind of what this formula is based on. All right, the slant height is really easy to find here. Again, it's like skiing down the middle of a face of that mountain. Well, if you're on a cone, any distance, any segment that connects the vertex to any point along the circle across the rim of the base here, they're all the same length. We define that to be slant height in a cone, and it works out really nice. The height, straight up and down height, is as you would expect, as it was in the pyramid. And this down here, which was kind of the job of the apothem before, well, now that's just really the radius of the circle. So we kind of have less different things to worry about here, just kind of like we did between the analogous same kind of simplification as we talked about between regular polygons and circles. Anyway, again, we're mostly going to study right cones. There are such things as oblique cones. They're really a mess to study. We're not going to worry about it. Volume's not bad, but surface area is no picnic. All right, so here's one of those unwrapped cones. If you were to, kind of unzip the base from the lateral area comes apart and it kind of looks like a Pac-Man. It looks like some sort of sector. If you were to cut out this Pac-Man out of a piece of paper and then tape these two together, you get a cone. This outer rim here would shrink up and be a smaller circle, and this would be a base, and this would kind of turn into a teepee, and this would be the vertex of the cone. That idea comes back on quizzes and tests, so be careful about that, and about where, how the flat, opened up, cut apart cone paper relates to the cone that we're looking at. Like this, it's like Pac-Man's circumference part right here. That would be that when it gets stuck together, that is going to be the circumference. That exact curve becomes the circumference of the base of the cone over here. So this circumference equals the length of this thing here, that kind of thing. This segment here, when you make a cone out of it, becomes the slant height. If you follow the path of what this turns into when you zip these together, that actually ends up becoming the slant height of the finished cone and that kind of stuff. These things will help you internalize or help us prove to you why these formulas are the way they are. The lateral area of a cone, so this whole area here, if you're looking at the entire cone, if you're looking at these terms on here where this is R, this is actually H, and this is L over here. The lateral area is half times P times L, like it was in a pyramid, but remember what P is here. P is essentially the circumference of the base, which here is a circle, which is 2 pi r. Half times 2 pi r times L, you can simplify a little bit and call it pi r L. I really don't mind if you just still think about this as half times P times L. It's not really a time saver to think of this. I don't know, maybe it is. I think it's another new formula to learn. This works perfectly fine. So either one of these is fine for me for lateral area of a cone. Some people really like this because it is shorter and a little faster, but I think it's another one to remember, and this is equivalent, so it's fine. Then again, if we're going to find total surface area, all we have to do is add on one base, and here that base is the base of the cone, this circular base at the bottom. All right, I'm about out of time. I'll do the problems in the next part.